Welcome to the video of my journey through ENPM809T Autonomous Robotics taught by Professor Stephen Mitchell at the University of Maryland, College Park. This course revolves around building an autonomous robot and participating in the Grand Challenge. This is a well-defined course taking into account path planning, localization, perception, and motion control. So if you are a fan of autonomous robots, this is a must-take course in the robotics program at the University of Maryland. In the beginning of the semester, we are given a kit which contains different parts to build the robot's body, a Raspberry Pi Model 3, B+, an IMU sensor, ultrasonic sensor, motor driver, Raspberry Pi camera, gripper arm, and a battery pack. Over the entire semester, we put together these components to build our final autonomous robot. We start with booting up the Raspberry Pi and making sure that all the required libraries are installed. In the first two assignments, we set up the Raspberry Pi camera to make sure that our robot is able to see the real world through the camera, which is an essential part of the robot's autonomy. In the third assignment, we are asked to detect green color from the given image of a traffic light which contains red, yellow, and green color. We detect the green color and draw a contour for easy identification. In the following assignment, things are getting a little more interesting as we are asked to detect the orientation of an arrow from a given image. This is a little bit tricky but interesting as we are taken deep into the concepts of perception. So now it's time to build the robot. So in the next session of the video, you can see us building the robot by putting together different components. As the robot's body is complete, we move towards putting together the electronic circuit where we integrate the battery pack with the motor driver and use the jumbo wires to make necessary connections to the Raspberry Pi to control the motors. For ease of mounting, I designed mounts for the ultrasonic sensor and motor driver, as well as fenders which are attached to the gripper arm to prevent toppling of blocks during the robot's movement, and 3D printed them at Terrapin Works. Now the robot's body is complete and we move towards building the gripper arm. It is a two-jaw gripper arm controlled by a servo motor. This is an essential part of the robot as it allows the robot to pick and place blocks at the Grand Challenge. This shows the teleoperation of the robot, which is just controlling the robot using WASD keys of your keyboard. Now we connect the ultrasonic sensor, which is used for obstacle detection. Here we can see the servo functionality by giving different PWM cycles. The following setup has been made to test the movement of the robot in a straight line and turning of the robot to different angles using encoders. A lot of issues were coming up while using encoders, and the professor helped us understand about different controllers to solve these issues. As we add the IMU functionality, as you can see, where we test out the different orientations, the robot becomes more robust in its movement. Now the robot is made to follow a rectangular path, but this time we turn the robot with the help of IMU sensors. As you can see, the turns are more accurate compared to encoders. The following graph shows the path taken by the robot, which resembles to a rectangle. All the perception techniques we have learned till now are put together to make the robot identify blocks of different colors and bring it back to the home position. After completing all the required tasks, our robot is finally ready with all the autonomy features. Now it's time to practice and test the robot's capabilities and make the robot ready for the final grand challenge. The Grand Challenge arena was open for practice, and the professor gave us all the necessary instructions. The Grand Challenge arena is a 10-foot square area with a 2-foot square area being the landing zone and the 4-foot square area being the construction zone. The robot has to start from the landing zone and collect different colored blocks from the cluttered environment in the order red, green, blue and place it in the construction zone until 9 blocks are retrieved in a 10-minute time frame. Each student gets 2 attempts and each run ends if the student decides to call off his run, or if the robot penetrates its boundaries, or if the 10 minutes time has been elapsed. Using the robot's camera, images of different colored blocks were captured from the arena to determine the HSV values for masking. The color picker code provided by the professor helped us in determining the HSV values easily. For 3 weeks, we practiced in and outside the class hours, day and night, to make our robot fit for the grand challenge. To make the robot completely autonomous, I wrote 600 lines of code, having different modules for localization, path planning, motion control, and perception. In my first attempt, after successfully placing the red block in the construction zone, the green block got stuck in my robot's gripper. This prevented me from picking other blocks and ended my first run. In my second attempt at the Grand Challenge, my robot was able to successfully pick up 8 out of the 9 blocks in the correct order and place it at the construction zone in the 10-minute time frame. Finally, my hard work and commitment saw a result as I was one of the top scorers in our batch. The Grand Challenge is the core component of this course, which tests your engineering skills and the concepts you have learned throughout the semester. This graph shows the trajectory followed by the robot in the second run, and these are the images of different blocks picked up by the robot from the robot's perspective. In the end, I would like to thank Professor Stephen Mitchell for organizing this wonderful course and guiding us throughout the entire semester.